Okay, so today's April 7th, and we're going to start off with section 1.3.3 in my notes on the type 1 and type 2 superconductors. And so what we had mentioned at the end of last time was that type 1 and type 2 superconductors relate to the ways in which magnetic flux can enter into a superconductor. So what we're going to see in this section is I just want to talk about the phenomenology of that. And talk about the phase diagram. And then in the in homework, not this one, but a future one, in a future homework, you will use gauge invariance and sort of path integral formulation to derive type 2 superconductivity. So what is the basic idea? So type 1 superconductors is simply what we've seen already, that the superconducting state expels magnetic field. And in fact, we'll see later on, probably today, that that's not really quite true. But it's a good approximation up to a thin surface layer. In a type 2 superconductor, the superconducting state in a magnetic field is able to support a periodic array of magnetic vortex lines. Or if you like, flux tubes. And we call them vortex lines because they're pretty much analogous to what happens in a superfluid, which is rotating. So in a rotating superfluid, you have quantum vortices. And these have a normal core. So in a type 2 superconductor, you have a normal core, which is threaded by magnetic flux. And then outside of that is the superconducting state. And so that's a different kind of picture. So let's look at what the phase diagram is that we expect to see. So this is the usual phase diagram of a superconductor. So it's in the H temperature plane. So somewhere around here is the critical temperature, and then what we've seen before is that there is a thermodynamic critical field, which I'll draw I'll draw it in like this. So that was a thermodynamic critical field. Now, in a type 2 superconductor, we're going to see that there's actually two other lines in this phase diagram. So there's a line that looks like this. And this line is called HC1 of temperature. And then there's a second line which comes in like this. And this line is called HC2 of temperature. And now let's label the various phases. So the phases here, this is the Meissner phase, where there's complete expulsion. In this phase here, this is the Abrikosov phase. Where you have an Abrikosov vortex array. And then outside of that, you have the normal state. And so this is our phase diagram for a type 2 superconductor. And what we're going to see a little bit later is we're going to look at the order of these transitions. So we're going to see that although this transition over here is a second order phase transition, we're going to see that this transition up here is also a second order phase transition, and we're going to work out exactly the theory that describes that in a little bit, and it's very different from what happens in this phase here, where this is a first order transition. So that's the behavior. Now in this phase, which is the Meissner phase, we know that the conductivity is infinity. And we know that in the normal state, the conductivity is, of course, finite. What happens in the Abrikosov vortex array state is that it depends. The conductivity depends on the on pinning. So I'm going to say that it depends on disorder, but in principle, sigma is equal to infinity, meaning that you do have you have off diagonal long range order and a real superconductor. So we'll talk a little bit about that. Okay, now let's talk about the phenomenology of this phase diagram. So first of all, why do you get flux tubes intuitively? And the answer that we're going to give is as follows. It's to do with surface tension. So if you have two phases, then they are separated by a boundary. So two phases are always separated by a boundary. And say like liquid gas, for example. And we're always used to the situation where that boundary is as flat as possible. And so that's usually as flat as possible. So that's the situation that we're normally used to. But that situation corresponds to a positive surface tension. So I'll just say such as a liquid gas. And exactly that situation applies in the type 1 superconductors too. So what happens in the type 2 superconductors? And I'm going to explain you how this works in today's lecture. We're going to see that the surface tension is actually negative. And so what does negative surface tension mean? Negative surface tension means that the interface between two phases tries to maximize the surface area rather than minimize it. So now you want a surface, an interface that is trying to become as convoluted as possible. But on the other hand, it can't get infinitely convoluted. And the reason for that is to do with gauge invariance. And what does gauge invariance do? Gauge invariance says that if I've created a small region of a normal inside a superconductor, it cannot, if I go around it, there has to be a topological invariant of flux that has to be satisfied, and you can't get less than that. And so what this gauge invariance does, it says that the flux through the normal part is quantized. And in fact, this quantization then says that, that when you work it out, the result of this interplay is that to minimize the free energy, we get a periodic array of quantized flux tubes. Now, people always talk about flux quantization. That's really not quite correct. So I want to just make this point as a caveat. So later we will see that it is really a different quantity that is quantized. And this quantity is known as the fluxoid. And I'm going to define that later. But for now, let's not worry about that. So just to record it. So the fluxoid quantum is called phi 0, and it's hc over 2e, which is about 2 times 10 to the minus 7 Gauss centimeter squared. Okay, so now let's talk about the magnetic response of superconductors.
Can I ask a question first?
Sure.
So the green writing there is saying that the negative surface tension means that the interface between the normal and superconducting regions wants to be as convoluted as possible. Why does, so the flux quantization restriction is saying that the area has to be some set value, right? So why does that stop the surface from why does that keep it from getting infinitely more wrinkled with, you know, area preserving deformations of the interface?
Well, roughly speaking, you're going to get little bubbles of flux in the material, and so you might say that I have just a very fine, infinitely convoluted array of these bubbles of flux, but they can't be infinitely small because of the fluxoid quantization. So the interface is not only wants to maximize itself, but also wants to sort of pinch off and form these little islands. So you can maximize your interface by having an interface that's not simply connected.
Okay, I see. Thanks.
Okay, yeah, good question. So let's talk about the magnetic response of a superconductor. So let me just remind you of some elementary elementary electrodynamics. So from simple electrodynamics, what you know is that the external field and the magnetic field that you measure, B, they're related by the magnetization, and I'm going to use units where this equation is written down in this way. So this is just a general constitutive relation. Kind of like what you have in an electric field with polarization. Now, so this is essentially an identity. Now, in the Meissner phase, what you have is that B is equal to 0. So there's no magnetic field that you can measure. There's an external field that is applied, but it is counteracted by the magnetization. And so since we know that B is equal to 0, because I've literally told you that, I haven't proved it to you, I've made it likely, but I haven't proved it to you, then what we can deduce is in the Meissner phase, the magnetization is -1 over 4 pi h. And if I were to measure the magnetic susceptibility, so the magnetic susceptibility is defined as dm by dh, and that is equal to -1 over 4 pi. And this is what we would call a perfect diamagnet. So this material, whatever it is, it finds a way to produce a magnetization that counteracts the external magnetic field. Okay, so so what happens in the vortex state? Then obviously there's more flux. And so that means that then chi is going to be greater than -1 over 4 pi. So let's draw the magnetic response pictures like this. So what I'm going to draw on the horizontal axis is H, and then on the vertical axis the field that you actually measure, B. So let's get our axes marked off. So we know that there's going to be the important scale HC1. There's going to be the important scale HC2. Somewhere in the middle is HC, which in fact really doesn't play much of a role. And then what we will see. Oops, let me use a color that you'll be able to see. So what we would expect is that B would be proportional to H in general. So let me. So this would be the line B is equal to mu H, which is what you would normally expect from material if it was, say, in the normal state. So what we know then is that above HC2 you actually do have a normal state, and so the relationship between B and H follows a curve like this. And then we know that what happens is that once we're below HC2 and between HC1 we have some magnetic flux in the system, but it's certainly going to be less than what you would have. You'll have more flux than you would get in the Meissner phase. So in the Meissner phase, you will literally have 0. So B will be 0, and then it will gradually rise up, and then eventually, once you get to here, it will be the regular relation like so. And so this is what you would see in a type. Excuse me, I'll just turn off. Okay, so this is what you would see in a type 2 superconductor. Now let's draw what happens in a type 1. So in type 1, what we have is that we simply have the Meissner phase up to the thermodynamic critical field, and then it jumps up beyond that to the behavior that you would get for a normal system. And so this purple line is what you would get for type 1. So that's the that's the magnetic response curve. And if I were to plot this not in B versus H, but in M versus H, let's draw that because it's quite interesting. So here's 4 pi m. Then again, my lines are HC1, HC, and HC2, like so. And now what we're going to get for the type 1 superconductor is it literally goes as minus 4 pi m up to HC. So we're going to get a curve that goes like this. And once you get to HC, then it comes down like so. So that's the behavior in type 1. In type 2, what's going to happen is until you get to HC1, it behaves just like a type 1 superconductor, and then gradually decays down to here beyond HC2, and then you get something like that. And so that's the so this is type 2. And this is type 1. Okay, so that's the magnetic response. We haven't said how it happens, but this is certainly what you would measure. Now, so let's make some comments about this. So you probably already guessed this, but remember we showed that the free energy difference between normal and superconducting state was equal to hc squared over 8 pi. So last time, that the free energy density was hc squared over 8 pi, and so the free energy difference is just given by this formula here. So of course that integral is this hc squared over 8 pi is what you get by integrating the magnetization dH, and so this is hc is hc squared over 8 pi, and it's the same for both type 1 and type 2. And so that tells you that there is some non-trivial connection between HC, HC1, and HC2. And we'll write that down later. Second thing I wanted to comment on is that the question of whether you have superconductivity in the vortex state depends on whether or not the flux lines can move. So think about this, you've got Faraday's law. So what that's going to tell you is that if the flux lines move, then they're going to generate an EMF. And so what that's going to mean is that there will effectively be a dissipation. And so that means that the conductivity will not be finite. So what that means is, how can flux lines not move? So flux lines can fail to move if they are pinned by impuritors. So I just say they can be pinned by defects. And so, so you have to worry about the disorder in a type 2 superconductor. But the other thing that's important to know is that the flux lattice has its own generalized rigidity. Just like the lattice of quantum vortex lines in a rotating superfluid. So in other words, if one vortex is pinned, by, let's say, a vacancy or impurity, the whole lattice is as well. And so, all that interplay is really quite complicated. Now, I don't know if I can do this quickly. Let me see if I can. The phase diagram, the magnetic phase diagram, of a superconductor is exactly like the phase diagram of vortex matter in a rotating superfluid. So let's see if we can quickly spot that. So where did we talk about superfluids? Millions of years ago, right? Let's see, there's quantum vortex lines. Yeah, found it. Okay, so remember this page here. Let's do something sneaky. See if this will work. There we go. Okay, so this is what we look at this. So this is what we have. What I just drew today. This is a magnetic diagram. And this is the rotating vortex. And so what you can see is that the angular momentum is very analogous to the magnetic field, and the external magnetic field, H, is analogous to the rotation rate. So let's write that down. I should do this the other way around, shouldn't I? Okay, so that's the connection. So we can think basically that that magnetic field is very much like the rotation in a superfluid. Okay, so I think that's where I'm going to stop with this general thing. So I want to just end with some general remarks. So this is the sort of the analogy. Between a superfluid and a superconductor. So this is really just superficial comments. So the first thing is that a superconductivity is essentially just a superfluidity of a charged fluid. The complication, though, at least for a superconductor, is that the superconductor is made out of fermions. And so what that means is that they have to form some kind of boson. And that's the famous Cooper pair. And so that's what we've talked about already in the case of helium-3, and for electronic superconductors. They first form this, and of course there's interesting questions that come out of this. Which are, for example, why do Cooper pairs form? And then, well, how do we do the many body theory of Cooper pairs? And to answer these things, we've done things in this part of the course in the opposite way to what we did in the earlier part of the course. So what I want to do here, let's choose this color. So we will later exhibit the instability. From the Schrödinger equation. So we'll basically do what is I forgot the name of the approximation. Never mind. That'll be a homework problem if I decide to give it to you. And then this one here is what BCS theory addresses, and that's what you're doing at the moment. You're going straight away in the opposite way that we did it historically in science. You're doing the many body theory first, but later on I'll show you. Well, I know it's basically an equation which in nuclear physics is called the Bethe-Salpeter equation, which explains how Cooper pairs form, and we'll just solve that by writing in a very simple way from the Schrödinger equation. So I'll show you that. So I want to talk about non-locality. So the average radius of a Cooper pair encompasses about 10 to the 6 other Cooper pairs in a weak coupling superconductor. So you can't really think of them as sitting close together in space. So this has two consequences. So one is that therefore Cooper pairs are clearly interacting. And so that's why you need the BCS many body theory to do that. And then the other thing is, because there are so many, namely 1 million, that implies that mean field theory works well. And so that was really very lucky for BCS. In those days, they didn't know really much about mean field theory and fluctuations and so on. So it turned out that this case that they solved actually turned out to be cell consistent and was essentially the best possible case. So we're going to see that BCS theory then is a mean field theory. Okay, so that's the general picture. So now I want to get into a more complete description, and so we're going to shift to a different section of the notes, section 4.10, and I'm going to talk about Ginzburg-Landau theory. Oh, you know what? I'm not going to do that. I've missed one thing. So wait, hold your horses. We're not going to do that. Do that in 5 minutes. I want to say something else about superconductors that I forgot to mention, and I want to mention, and that is the Josephson effect. So the Josephson effect is very simple. You can make you make a junction, and all that is a normal metal or non-superconducting sandwiched between two superconductors. Okay, so it looks something like this. I'm going to make this bigger so you can see it's better. Sorry. So there's two superconductors, and then in the middle is some normal stuff like that, and then you connect this thing up to an electrical circuit, like so, and what you find is that if I've got a voltage V between the applied across these two superconductors, what you get, much to your surprise, is that you get a uniform V gives rise to an AC current, and that's called the AC Josephson effect. There's another thing you can do in which you can get a what's called the DC Josephson effect. And that DC Josephson effect is basically a DC current without an applied voltage. Roughly speaking, and we're going to see, these things have traditionally been understood from the point of view of tunneling of Cooper pairs. And what we will do here is we will explain them from the point of view of gauge invariance. So this is actually one of the very few instances in the history of science where somebody who was a great expert was very wrong about something, and that was John Bardeen, who didn't believe in the Josephson effect when Josephson invented it. So Josephson was a graduate student at Cambridge University in the 60s, early 1960 or so. Phil Anderson was lecturing there, and the story is that Josephson came up with this during Anderson's course similar to this, and essentially understood pretty much everything there is to know about the Josephson effect very, very quickly, all by himself. Because he was formulated in terms of the tunneling of Cooper pairs, Bardeen didn't believe it, because the tunneling of Cooper pairs requires the tunneling of 2 electrons, which would be a second order or higher order process. And what he didn't understand in those days was the idea that you can have a macroscopic wave function which is quantum coherent, and so the electrons actually for a Cooper pair tunnel at the same with the same order matrix element as a single electron does. And so that's how the quantum coherence is what enables this Josephson effect to occur. So we will talk about that a little bit later from the point of view of gauge invariance. Okay, so on to Ginzburg-Landau theory. So what we've seen in the course up to now is we started off with looking at weakly interacting bosons. We saw that we could derive by various many-body theory, field theory methods, we could derive the existence of off-diagonal long-range order. We saw that we could calculate the excitation spectrum, and then we from that we derived a macroscopic description, which is the Gross-Pitievsky equation. So what we're going to do now is, although in homework you've worked out the microscopic theory of superconductors from BCS, we're going to pretend that you hadn't done that. And we're going to ask, how would we go about describing a superconductor without bothering to go through the microscopic theory? In other words, can we write down the analog of Gross-Pitievsky equation, the macroscopic picture, without having to go through the very detailed calculations that you need in order to derive the Gross-Pitievsky equation from a microscopic theory? And so the answer is that you can, and in fact that was done before BCS theory in 1950 by Ginzburg and Landau. So let's just say then, in 1950, Ginzburg and Landau proposed a top-down macroscopic description of superconductivity, and you know it wasn't perfect. I mean, for example, they didn't really understand what was the object, the wave function that they were dealing with. So this is a sort of analogous to the Gross-Pitievsky description of a superfluid. And in this description, there was some kind of sort of superconducting wave function, which was not really defined. And there were things in it that needed to be ad hoc, and as I'm going to talk about that. So you're going to see that there was a coupling to the electromagnetic field, but that involved a mysterious factor of 2 in order to agree with experiment. And that factor of 2, in fact, is the effect, is the place where Cooper pairs come into the theory. So this is, in fact, later understood to be where the existence of the Cooper pairs arises in this description. And what was the main use of this description? Well, as we talked about before with Gross-Piotrowski, it's a very good description of spatially varying superconductors. So the other thing that I want to mention is just while we're talking about the historical note, is that the Ginzburg-Landau theory was not well known in the West. What's happened there? And why was it not known? Well, the date was the 1950s, and this was the time when this was the McCarthy era of anti-communist sentiment. And so what happened was that that the U.S. authorities would in fact intercept copies of Soviet physics journals, and they would throw them into the sea. And this was described by Phil Anderson in Parks's book on superconductivity.
Could I ask, was that the case for all countries, like Western countries?
No, probably not. But it was true in the U.S. and for most of the time that was really where the action was. At least in the 1950s at University of Illinois and other places. So there were other things going on, particularly in Cambridge in England, but it really was the US that was the dominant place there, and this is where it would have been very helpful if people had understood this connection. And so let me just say that in 1958 and 59, Gorkov showed how to derive Ginzburg-Landau theory from BCS, and I think he even claimed to have done what BCS did before them, although nobody outside of Russia believes that. So this was a very interesting period, and it's quite interesting to see how the lack of scientific communication really did hold up science. Okay, so that's the history. So what is our goal in this section? So what I want to do is now derive the theory. When I say derive, I really mean i.e. motivate it. And then we will use it to study the spatial structure of type 1 and type 2 superconductors. Just as we did with superfluid helium, we'll look at the solutions for vortices. So let's start off then with a uniform system. And we're not going to say what the wave function that we're going to write down really means. Later we can talk a little bit about that, and you'll understand where it comes from as a matrix element, just as we did in superfluids. But for now, we're going to pretend that we don't have any of that. So we're going to suppose that there is some kind of superconducting wave function, and we're going to define it so that its norm is half the number of superconducting electrons. So we're going to say that near TC, we expect that psi is small, and so we can make some kind of expansion in the powers of psi. And just so that you know what this thing is, in Gorkov's theory, what he shows is that this psi is actually proportional to the gap function in superconductivity. So you'll derive the equations for the gap function in the homework, and those are the equations that really define what psi is. Okay, so then what we're going to say is that the free energy of the system is just the volume times the free energy density, and what we're going to then say is that we can write down the free energy density in the superconducting state is the free energy in the normal state plus a contribution that comes from the wave function, and we're going to write that contribution as alpha times psi squared plus beta over 2 psi squared squared. So why do we write it in this form? Well, what we know is that the free energy must be independent of the phase. In other words, it has to be a scalar. And so psi squared and psi to the fourth are the only, the lowest order rotationally invariant scalars.
What rules out grad psi terms?
Spatially uniform. Okay, so we're just talking for now about spatially uniform. Okay, in a minute I'll put in gradient terms. Okay.
Mm-hmm.
Okay. So so then what do we need? Well, in equilibrium, the free energy is minimized in equilibrium. And so that means that obviously we need beta to be greater than 0. Otherwise, the free energy would not be bounded below. So we need beta to be positive, so that Fs doesn't go to minus infinity as psi goes to infinity. So we want to restrict that kind of solution. So the coefficient alpha can be any sign you like. So it can be greater than 0 or non-zero. So let's draw what the free energy will look like. So I'm going to draw the real part of the order parameter, the imaginary part up here, and then the free energy in the superconducting state. And I'm going to do that for both alpha greater than 0 and alpha less than 0. So let's first of all do the case when alpha is greater than 0. So then what will happen if alpha is greater than 0, then this is the functional form for the free energy is just x squared plus x to the fourth. So it's going to basically look something like this. So this is the origin over here. So this is the case when alpha is greater than 0, and its minimum is at the psi is equal to 0. So this corresponds to t greater than tc. On the other hand, if I have alpha negative, then what I get is something different altogether, and I'm going to probably completely screw up my drawing of it, which I inevitably do the first time I do it. So please bear with me if I have to do several attempts to get it to work. So there we go, something like that. So what I hope you can see is that this thing looks like the bottom of a wine bottle, and it has this this minimum at along this red curve. So this is a curve of degenerate. like so. And if we work out the equation for the free energy, so the equilibrium value of psi is given by df by d psi is df by d psi star is equal to 0. And so what that tells you is just differentiating that psi squared is equal to minus alpha over beta. And so if alpha is negative, so let me just say it's either this or psi is equal to 0. And if alpha is negative, then I can have the solution psi is equal to the square root of minus alpha over beta, but the phase is indeterminate. And so you have a continuum of solutions that are degenerate. And if alpha is greater than 0, then the only solution is that psi is equal to 0. So that's what the solutions look like. And so what that means is that the difference between the superconducting and normal free energy densities, well, we already saw that was equal to hc squared over 8 pi. And so we've learned that that is equal to minus alpha of t squared over 2 beta, just simply plugging in the value psi squared is minus alpha over beta into the functional form over here for the Ginzburg-Landau free energy. So what that then tells us is that we can deduce then that alpha of t is proportional to the thermodynamic critical field hc, and as hc of t goes to 0, as t tends to tc. And so what we will do is that we will generally expand alpha of t around tc. So alpha of t is written down as some constant times t minus tc over tc plus higher orders in t minus tc, like so. So this, as is always the case in these sort of second order phase transition problems, the coefficient of the quadratic term scales linearly with the difference between the critical temperature and the temperature that you're at. Okay, now somebody asked about spatial gradients, so let's finish off today's lecture by putting in the spatial gradients. So what we expect is that there should be an energy penalty for spatial gradients, and it's got to be isotropic and phase invariant, and so and also analytic in psi. Now, I just want to make a comment about the analyticity. So the answer to this is yes, we want analyticity. And why? Well, let's go back to the first lectures in the course. So early on in the course, we discussed coarse graining. And because we're coarse graining our system, coarse graining means that we are taking a finite number of degrees of freedom in our coarse graining scale. Now, Ginzburg and Landau weren't really thinking about coarse graining and those sorts of things at that time, but today that's exactly how we would interpret this. So today we would interpret psi as a coarse grained version So I'll say some quantum operators because I'm not going to be very specific. And so that means that psi itself, that the free energy expanded in psi is going to need to be analytic. And that's why we chose these we did a Taylor expansion of the free energy. And so those considerations mean that the way we construct the free energy functional of psi of r is, as we saw at the beginning of the semester, as d3r 1/2 kappa magic psi squared plus the superconducting free energy that we just wrote down. So that is the Ginzburg-Landau theory. As we've talked about, and so let's just finish off by describing what are the coarse graining scale. Is lambda, which must be much larger than psi naught, the size of a Cooper pair. So basically, what we want to make sure that we have some Cooper pair size, and then we're looking at psi on a scale much larger than that. So it's slowly varying, and so that's the natural scale where we expect this description to be adequate. Now, what we're going to do next time, and I don't have time to start it today, so next time, what we're going to do is we're going to include magnetic fields. And so what we're going to see is that where we had the phase of the wave function, that's what we had before in our superfluid theory. That phase of the wave function, well, what happens is that the phase gradient gets replaced by a covariant derivative, which I'm going to write like this. And so when we write down the Landau theory, we're going to have in it the electromagnetic vector potential as well as the wave function. So we'll talk about this so-called covariant derivative. And then this describes the electrodynamics of superconductors. So that's where we're going to stop for today's lecture. So let me